is coming. So for now, I think I will continue with the discussion on trust. Okay, trust. Anyone here knows what is trust? Any of you? I believe some of you uh, have. Any of you? Uh, I believe most of you knows about your parents' occupation. Uh, any of your parents works in the oil company or in the service company?
Mine, sir.
Yep. Where, sir?
In Konoko.
Konoko. Okay. So, have your parents have your parent told you about his job there? Sir?
Yes, several times.
What is main job there?
He's actually a project cost control advisor.
Cost control advisor. Okay. Yeah. Maybe it still has some relation because when talking about a building a brick like that, most likely your parents will be involved as well. Okay, in the oil company or in the service company, normally if we work there, we have to deal with a trust system like this. Okay, this is a trust system where which is available in the oil. Normally, it's there in the oil company. Okay, when we talk about trust, is I believe you have seen this kind of structure, right? Something like this. Actually, it's not just available in trust, but in the in, uh, what you call it, in the bridge as well. In the bridge, you will see this kind of structure, right? Something like this. Uh,
Also in cranes, right, sir?
yeah, sorry.
In cranes.
Yeah, crane as well. Crane, bridge, something, bridge like this. Okay, and in the offshore structure, yes, crane as well, yes. So this kind of infrastructure is everywhere actually. So infrastructure, if you ask me what is infrastructure, is actually uh, the structure which is only consists of two force member. What is two force member? I will explain to you after this. So you can see this is the normal bridge. Normal bridge structure is normally like that. And I believe I believe you've seen it before. Okay, some bridges have structure like this, like that. Especially those bridges where it's mainly made of steel. The structure is made sorry steel, metal. Okay, okay, where the structure is mainly made of metal. Some other bridges, the structure is mainly made of concrete, and there is a pillar like that. Okay, but most of the bridges have structure like this. Correct or not? I believe you have seen it before. Right?
Yes, sir.
Okay, the same as this one. This is a big bridges. This is big bridge, and actually it consists of a truss as well. You can see it. Here there is a lot. There is a truss there, and here there are a lot of trusses as well. So it consists of truss. So uh, trust structure is something which is consists of all of it are two force member. Okay. How can we differentiate two force member with the other member? And the other member is you can see slender member join together at their end points. You can see, right? So in comparison to the bridge size, the member here, okay, the beam, not the beam, the member here actually is quite slender in comparison to the whole bridge size, correct, right? And each member is only connected at the end of it, only. Each of those members are only connected at the end of it, only. Okay, this kind of structure, you've seen it everywhere, and we call it as truss structure. Okay, the same as this one. You can see there are a lot of members there. This is one of it. This. Okay, and all of those are connected only at the end. Okay, at the end of the member. So all the connection are happening at the end. So there is no connection in the middle. That's why we call it a truss structure. Okay. Anyone here still be confused about what is truss structure? If yes, please let me know, and I will try to explain, try to elaborate a little more.
Sir, so the meaning of the definition of slender in the itu is the tiang-tiang ya, sir?
Yeah. Slender member, yeah. The meaning of the slender member is this one. Satu tiang ini itu adalah satu member langsingnya. Ya. Oke, satu membernya. Nah itu member itu maksudnya itu. Satu tiang-tiang kecil ini. Itu maksudnya member. Nah, si tiang-tiang itu disambungkan hanya di akhirnya saja, di bagian ujung-ujungnya saja. Nah, yang seperti itulah yang disebut sebagai sistem struktur truss. Okay, that's why you have seen it everywhere. You have seen it in the beaches. You have seen it when you see crane, and then in the oil structure, in the onshore or offshore oil structure as well. It's everywhere. Okay, so there are a lot of structure there, which is using truss. There are a lot of truss structure out there. Okay. But the most important thing about truss structure that you're supposed to learn is what is so special about it. Okay, whenever we talk about truss, okay, each member, each of the just now another called as it's tiang-tiang, okay, tiang. Okay, each of the member, okay, atau tiangnya ya, can only withstand either tension force or compression force. It cannot withstand bending. It cannot withstand force, other directional force, other direction, other force direction. So it's either tension or compression only. That is what's so special about truss. And we call this kind of member as two-force member. Why we call it as two-force member? Because the force only happening at both ends only. Okay, only at both ends, and the direction is either tension or compression like this. Okay, that's the first special thing about truss. So all the member, seluruh tiang-tiangnya, okay, all the member, okay, is must be a two-force member. So must be like this. Then the other assumption that you're supposed to know when we talk about a trust system is all the loading are only applied at joints. Okay, all the loading only apply at the joints. That's why the force is happening at only the end of the pin, the end of the member. Okay, and beside that, we always assume that the members are joined together by smooth pins. Okay, so sometimes we have something like this, right? If we assume everything, if we assume that the structure is truss, okay, this kind of joint, we have to replace it by smooth pins. Because in our truss analysis, everything is simplified, so smooth pins must be assumed like that. Any question about the definition of truss?
I'm sorry, sir. I would just like to
Okay.
make sure.
So
the truss design itself doesn't relate to the materials, right? So if it's a wood, it's still called as truss as long as it's the structure itself.
Yeah. Unluckily for you guys, you have never been to the Aula Barat or Aula Timur. West Hall, our ITB West Hall and ITB East Hall. Those two halls are very famous in Indonesia because it's a very old hall, very old aula. Okay, and some part of it having a truss structure, which is made of wood. Okay, Irfan. So it's not necessarily have to be it is not necessarily have to be from metal like that, from wood as well, or from other kind of metal is supposed to be okay. So it's more towards the type of the load which is happening at each member. That's the thing. So the main definition of truss is a structure a structure where all the member, all the pins, or all the member, okay, all the member must be two force member. That's the definition of truss.
I see, sir. Okay, thank you, sir.
Yep. Okay, that's the definition of truss. Okay, all the member must be two force member. Any other questions before I go straight to the main problem that we have? Okay,
Sir,
I will
I want to ask, these
Rafi?
smooth pins,
Mm-hmm.
do they have like
what do you mean by wood pins?
smooth pins?
Oh, smooth pins. Yes, yes.
Yeah. Do they have like a specific properties that differentiates them with like other, like say nuts and bolts or something like that?
Okay. Actually, nuts and bolts, we can sometimes we can assume it as a smooth pin as well. Okay, because smooth pins is the easiest assumption that we have. Why it's easiest? Because when we talk about smooth pins, okay, for example, it's like this. If we have a beam like that, at one end, it's we put the smooth pins there to the wall. Okay, at the other end, there is a roller there. Okay, if we are talking about smooth pins here, okay, because it's smooth, it will not give you a moment reaction.
Oh,
So
I
because
see.
it's smooth, okay, it will only give you a horizontal or vertical forces. That's what's so special about smooth pins. That's why in statics, most of our assumption, unless it is mentioned before, okay, we always assume that it's a smooth pin. So whenever we talk about pin, we always assume that it's a smooth pin, unless it's mentioned otherwise. So
Okay.
if it's mentioned that, oh, the spin is not smooth, it's welded, okay then. In that case, you have to put a moment there. The same problem as what we discussed yesterday, I believe, right? Or last week, I believe. You get it, Rafi? So the
So
first assumption must be smooth,
okay.
unless it's said otherwise.
So the most important property of the smooth spin is that it does not cause moment, yes, sir.
Yes, correct.
All right,
Yes, correct.
understood.
Any other question? No? Okay, then in that case, I will continue.
Sir,
Yeah.
by all loadings are applied at the joints, do you mean the two force? Does this mean the two force member?
Yes, correct. So,
Oh, okay.
In thrust, okay, whenever we talk about thrust, okay, all the loading is only applied at the joints. Okay, there will be no option of the loading is put in the middle of the member like this. So it is not a load in thrust. So whenever we have things like this, then we cannot consider it as a thrust anymore. Okay, Matthew?
Okay, so it must be at the ends, yeah, or the
Yes.
joints.
Yes, must be
Alright.
at the end, must be at the joint. Yes, correct.
Okay,
Because
thank you, sir.
for when we talk about thrust, right? All the member must be two force member, and two force member, we only have a force at the end only. That's why the loading must be happening at the end as well. Okay, this is another example. Simple thrust. Okay, when we have this kind of things, okay, this is the simplest thrust. Okay. As you can see, by definition, the loading is only happening at the ends only. You can see it. It's happening at point C. Okay, the point C there is the end, right? One of the end for member AC and member BC. Beside that, there is a loading as well happening at point A and point B, correct? So the loading there is only happening at the end only. Okay. Then we add two more redundant member here. Why I call it as redundant? Because later, after I told you guys how to analyze it, you will know that this and this will be zero force member. But it will be later after I teach you how about this. Okay. The first thing that we're supposed to learn about the thrust is how can we analyze it? When we have a thrust system, for example, a bridge like that, okay, simple bridge like this, for example, okay, pin at one end, roller at the other end, okay, simple bridge like this. Then we know that there is a load to car or something like that, 10 kilonewton, for example. Okay, when we talk about this, right, we're supposed to know what forces happening at each member. Why? Because normally each member has the maximum capacity, the maximum load where it still can handle. If it's more than that, if it's more than the capacity, if it's more than the maximum load that it can handle, that particular member will break. Okay, that particular member will break. If the member will break, if the member breaks, okay, the structure will collapse, and we don't want that. In statics, we don't want that. Okay, that's why it is very important for us in the trust analysis to know about the forces which is happening at each member. Okay, do you get it, guys? Answer me, please. Don't just stay quiet.
Yes, sir.
Okay, good. Yeah, do you understand? Yeah.
Sir, I want to ask. So if
Who is this?
Azhar Nanda.
Okay, Asar. Yes. Yeah,
Um,
Asar. Okay, Asar.
yes. So if one of the joints collapse, all of the structure will
No. We are not
collapse too,
talking
or
about joint which is collapsed. We are talking about member.
member?
Okay. Yes, of course, the joint will have the maximum load where it can withstand as well. But we will assume that the joint is perfect in our calculation, always like that. That's why in this case, right, we try to take a look at the forces which is happening at each member. Okay, and if the load there is more than its capacity, the member capacity or the member maximum load where the maximum load where the member can still handle. Okay, if it's more than that, then it will collapse. That particular member will collapse. But when one member is collapsing, the rest will be collapsing as well. Because it will be a sequence like that. When one member is collapsing, and when one member is collapsed, okay, there will be no load there anymore. So it will not be able to withstand load anymore. So it will affect the other member as well. The load where the load that the other member must withstand will become bigger as well. So most likely, in that if that things happen, the other member will collapse as well. That's why when you see a bridge collapse, sometimes it started with one member, then the rest will follow up. Do you get it, Asad?
Yes, I get it.
Any other question before I following up with this? So for today, I will just explaining about how can we handle it, how can we find out the forces which is happening at each member. Then after I tell you about the way to find it, then we will practice maybe one problem, one or two problem. Then after that, I will give you homework for you to practice by yourself about this trust system and equilibrium as well. Because I believe some of the problem I haven't given it to you, more advanced problem of the equilibrium and basic problem of the trust. That's your homework for that's your next homework, and the due date will be on next Thursday. Okay, I will continue. As I told you, it is very important for us to know the forces which is happening at each member. Okay, and for example, we have this kind of structure. Okay, we have this kind of structure, and it's loaded at the at point B, 500 Newton to the right, like that. And at point A, it's pin joint. At point C is roller joint. Okay, and the question there is, I want to find out the forces which is happening at this and this member. Okay, how can we find out? The answer is simple, because I told you from the beginning that each member in the truss structure can only withstand either tension or compression. As I stated here, right? Only tension or compression. Okay. Okay. At each member, it can only withstand only tension or compression. Then we know exactly where's the direction of the force. Okay, the direction of the force which is happening at member AB and member BC is either tension or compression. So, because it's either tension or compression, we know the direction as well. If it's either tension or compression, the direction of the force, okay, the line of action of the force will be at the same line as the member, same as that, AB, member AB. So the direction of the force will be the same line as member AB. The direction of the force which is happening at BC will be the same line as the member BC. Okay, so the direction of the force will be there. Will be this at the same line at the line of action will be at the same direction as the member. That's why from this we know several important information that first FBC, the direction will be 45 degrees. Okay, and FAB, the direction will be vertical. Okay, because of that, because we already know the direction which will be happening at each member, because it's always tension or compression, then just for the truss structure, we can try to analyze the joint, the forces which is happening at the joint. Because like it or not, static equilibrium will still be happening. So for example, if I analyze joint B, okay, if I analyze joint B, of course there will be 500 newtons to the plate. Beside that, at joint B, joint B is the connection of member AB and member BC. So for sure, there will be effect. There will be in effect there. There will be a force there, which is happening due to member AB and a member BC. And how can we know that? Okay, then I will always assume that. Okay, I assume that there is a force due to member AB and the direction is tension. And there is a force due to member BC, and the direction is 45 degrees. Just now AB is vertical. Now BC is 45 degrees. Okay, I assume it as tension. If you see this, okay, actually we can use something like this or something like this as well, because from the beginning we can just assume either the member is under tension or under compression, because the option is always each member is either under tension or under compression, like that, or there is no force there, zero force member. So the option is only this. But for us, in order for us to analyze it correctly, we cannot assume from the beginning that it's zero force member without any proof. That's why we always assume either under tension or under compression. Here, I assume everything is under tension. Can we do that? Yes, we can. Then what things that we supposed to do after that? We have to solve it, of course. How can we solve it? Okay. How can we solve it? We can solve it using equilibrium equation, of course. Okay, now, just now, Rafi. Hello, Rafi.
Yes, sir.
Which equilibrium equation that we can use to solve this particular problem? The free body diagram, the point B here, the one that I draw just now.
We can use sigma fx is 0 and sigma fy
Okay,
is 0.
sigma fx equal to 0, sigma fy equal to 0. Can we use sigma moment equal to 0?
I don't think so, but I'm not sure.
Yeah, oh, you have to be sure, because it is not possible to use sigma moment equal to 0, because all the forces are happening at the same point, right?
Oh,
At
yeah.
point B.
So
So
there's no
it will
moment
be useless.
for
Yes,
this.
there will be no moment. There will be no momentum. So it will be useless. So we can use that. We can't use that. So we
Okay.
have to use sigma fx equal to 0 and sigma fy equal to 0. Okay. By
Alright.
using sigma fx equal to 0, what we will have there? What equation that we have there? Okay.
It would be 500 plus
Hmm.
FBC, the x component of FBC.
Yeah, f component of fbc is supposed to be what? fbc multiplied by
Multiplied by
cos 45, right?
cos 45, I think. Yeah,
Yeah, cos 45 and sin 45 is just simple. Equal to 0.
equals 0.
Can you help me to solve for fbc here?
Hold on. Would be 500 over cos 45. Yeah.
Yep.
707.1.
707.1.
0.1.
Minus or plus? Minus, right?
Okay, because it's going the other way here.
Yeah, minus.
Okay.
Newton. Why we have minus there, Rafi? Can you guess it?
Because the 500 is going to the right,
Mm-hmm.
and in order for the equilibrium to occur, the other force has to be going the opposite direction.
Yeah, so FBC is not supposed to be going to the bottom right, it's supposed to be going to the top left, right?
Top left.
Yeah. So actually, our first assumption is not correct. It's okay. As long as we know that if it's negative, okay, if the value here is negative like this, okay, it means that our first assumption is not correct. So the direction is supposed to be the opposite of our first assumption. So in this case, the direction is not supposed to be tension, but it's supposed to be compression. So BC is supposed to be under compression.
Okay.
Okay, do you get it, Rafi?
Yeah, I get it.
Yeah, FVC is supposed to be under compression. So the force at point B is supposed to be going to the top left instead of top right. But you don't have to fix this anymore, as long as you put the explanation there as compression is supposed to be okay. Okay.
Okay.
Yeah. Thank you, Rafi. Oh yeah, one more thing, Rafi, because you already solved this. How about sigma Fy equal to 0? What we will have that?
Sigma Fy equals 0. We would have 0 equals to FAB plus
F equal to FAB plus FBC sin
FBC
45.
sin
Right?
45. Yeah.
Right. So we will have FAB plus FBC sin 45 degrees equal to 0.
Yes.
Do we have the value of FVC?
We do from the other equation
Yeah.
that we made.
What is the value there?
Minus
Minus.
707.
Don't forget about the minus, because we use the same free body diagram here, right?
Yeah.
Okay, so don't forget about the minus. So we have FAB plus minus minus 707.1 Newton sin 45 equal to 0. So here what we will have will be equal, FAB will be equal to 707.1 sin 45, right?
Yeah.
What is the value there?
Uh,
500, correct?
Should be.
Yeah, 500 Newton. Positive. So FAB is correct, it's tension. FPC is compression. Tension is P, compression is C. You can just put it that way. Okay, 500 Newton tension, FAB. FPC is 707.1 compression. Do you get it?
Yeah, I get it.
Good. Okay, so we can solve
Sir,
for that. Yeah.
I'm still confused why if BC is towards B, it's called compression, and when
Okay,
BC
it's
is
very good question.
alright.
Yeah, it's very good question. Wait. Let me find out. Okay, just use. I think I will just use this one. I need another slides here. It's not updated. Okay, then it's okay. Oh, just now your question is why, if we use F Y tension is in that direction and compression is in that direction.
Yes, sir.
Okay, so it's like this. Please don't try to take a look up and just use it. Okay, I will just use this thing. Okay. When we have a member like just now, it's supposed to it's supposed to be like this. Then like this. Hey. But then anyway, if I have member like this and like this, then here we have a rollout. Then here we have a pin. Okay. The question is why just now the forces is like this. The free body diagram will come like this, and this one is tension A, B, C, right? And then this one as well. The direction is slightly changing. It's okay. I will just use the current one. F, B, C. Tension as well. Why tension in this particular things is in that direction? That's your question, right? Matthew. Hello, Matthew. Where is Matthew?
I'm here. I'm thinking.
Yeah. So actually, it depends on where we see it, Matthew. So when we take a look at the member, for example, I use the member AB here as example. Tension is supposed to be like this, right? Correct or not, Matthew?
Yeah.
Okay, this is our FAB. But remember, we are not looking at the member, but we are looking here. This one, this particular free body diagram is the join. Okay, let me draw another one. Sorry, let me draw FBC as a member BC as well. Okay, in this case, the assumption that I have here is BC is under tension, so it's supposed to be like this, right? Correct, right?
Yeah.
Okay, it's under tension. But why the direction in the joint is like that? Because it's action and reaction. It's for everyone. Okay, it's action and reaction. Okay, try to take a look at this. This is member A, B. Sorry, this is member BC. Okay, okay. Member BC is being pulled. That's why that's why he's under tension. That's why member BC is under tension. Okay, but if we take a look at the joint B, this is joint B. Okay, member BC is actually pulling the joint B as well. So they are pulling each other. Okay, joint B is pulling member BC. Member BC is pulling joint B. That's why if we take a look at the joint B, okay, the joint B there, at joint B there, okay, the BC, member BC is pulling joint B. That's why the direction is like this. Because its tension is pulling. But on the opposite side as well, it's correct. Okay, sorry. Member BC is being pulled by joint B. That's why the direction is like that. So this and this are action and reaction, Matthew. Do you get it, Matthew?
Yes, a little bit.
Yeah. So by using joint method, we are trying to see the joint. We are not looking at the member. We are trying to see what is happening at joint B here. Okay. So at joint B there, what we try to see is what forces happening at joint B. So besides 500 Newton, what else? We can see that at joint B, each member is giving a force at joint B, and the force is depend on the assumption. If we assume that at joint B, okay, if we assume that BC and AB both is under tension, then both is supposed to be pulling joint B. Pulling joint B. So whenever we talk about a tension at joint, okay, we always see that the force is going further away from the joint. So you can see it, joint B here, and FPC is under tension. That's why the first FPC is going away. AB is under tension as well. Our assumption is AB is under tension. That's why FAB is going away. Okay, but the opposites, we can say the opposite as well. Okay, if we assume the AB is under compression like this, and BC is under compression as well, like this. Okay, and if we take a look at joint B, okay, we said 500 Newton force there. Okay, the forces due to member AB and member BC is not going away because it's compression. Compression means the member compress the joint, pushing the joint. So it will be going in. The forces there will be going in. FBC. This is under compression. Do you get it?
Sir, in short, can we just assume the other, let's say there's BC, right?
Mhm.
Because B is the joint, can we just like CC if like this compression at C point, there's a force towards the B. So compression is towards the B.
Oh yes, correct. The same.
Is that fine?
Yeah, that's fine.
Okay, so
Or
if,
you can think as well that if it's compression, when we talk about joint, when we see the joint, okay, the forces is always going towards the joint. It's compression. If it's
alright.
if it's tension, that the force is always going away from the joint.
Will this change the fact if 500 newtons is to the left?
No. It won't. 500 newtons is given, right? It's outside force. So we will not change that.
Okay.
Because
Thank you.
this one is just assumption, right? Matthew, you can assume anything. You can assume the FAB is compression. You can assume the FAB is tension, like this. Like what I told you before, FBC under tension as well, like this. You can assume it this one as well. But later, after you calculate using sigma fx equal to 0 and sigma fy equal to 0, we cannot use moment in joint method because we only consider one point there. So we cannot use sigma moment there. So by using these two equations, you can solve for FAB and FBC. And if the value is negative from your previous assumption, okay, it means that your previous assumption has the wrong direction. But you don't have to correct it anymore. So just state it there that, oh, the direction is the opposite of what you drawn. Like that. Do you get it, Matthew?
Yes, I see, sir. Also, last question is, if we calculate the tension for, let's say, FBC and the value is negative, can we assume that's positive compression force?
Yeah, it's always you can do it that way, but I always prefer because this is the normal standard in statics and in mechanics of materials. Tension is always positive. That's the standard. Whenever we talk about tension stress, tensional stress, when we talk about tensional force, the positive is always tension. So
I
that's
see.
why whenever I draw it, I prefer drawing it this way. Assume everything is under tension. Why I assume everything is under tension? Because that's the normal positive way. So when the value is negative, then it means that it's compression. That's my style, but it's up to you. Okay?
I understand, sir.
So
Thank you.
basically, sir, if we encounter like a compression in the problem, we could just assume it as negative tension.
Yes, compression is always negative tension.
So we could just like convert it. If the question says compression, we'll just like assume negative tension like that.
No, because from the beginning you can always assume as you like. So from the beginning you always assume that okay, because normally the given problem is like this. The given one is only the external forces, and where is the joint? In this case, is spin. Sorry, this is spin and this is roller. Okay, so you can always assume each member is under tension or under compression from the beginning. That's what I normally do. So, not that what I normally do, but that's what normally it is. The problem is normally it's like this, and the problem is always try to determine the force which is happening there. Sometimes you are only asked to find one member, the force which is happening at one member or two member, right? But sometimes you are asked to find all the forces which is happening at all members. Okay, that's why for me, it is easier for me to always assume that all the members are under tension.
I
You
see.
get it, Asad?
Yeah, okay. I get it, sir.
So this is one of the examples. Determine the force in each member of the loaded fast. Okay. For this problem, what we're supposed to do? This is the only practice problem that I will give before giving you homework. For this particular problem, what we're supposed to do to solve it? You are asked to find out the forces which is happening at each member.
Can I try, sir?
Who is it? Matthew?
Yeah.
Yeah, you can.
So we first see two beams BC and DC, because it's the first beam that's affected by 5,000 newtons.
Yep. Actually,
And
there are several ways, Matthew. Okay, that's a good thing you started from that point. But sometimes some of you want to solve for the external forces which is happening at point A and point B. Right? It can be done, right? Solving point A and point B. AX, AY, which is happening at point A, and BY, which is happening at point B. Actually, it can be done as well if you use the free body diagram like this. Okay, there will be BY, there will be AY, AX. Okay, so you can solve for BY, AX, AY using sigma fx, sigma fy, and sigma moment for this particular free body diagram. Sometimes you still need to find out the external, all the external forces like this first. But sometimes you can solve it directly. And this is one of the problem where we can solve it directly, like what Matthew said just now. Because by solving point C, by solving a joint C there, right, we will be able to find out FCD and FBC. Correct, Matthew? Correct or not?
yeah, the force will be at the opposite direction of AX and AY, right? Tension
XAY,
force,
no.
tension
You cannot say it that way, because to solve for AX and AY, you have to use the this particular free body diagram. Now it has no relation with this one. Maybe. Okay. But the question is not AX, AY, and BY, right? Yeah. The question here is to
No,
determine.
what I meant
Yeah.
is using the first diagram that you have
Oh,
drawn.
okay. Yeah.
We can find the value for AX, AY, and BY.
And BY. Yes, using sigma Fx, sigma Fy, and sigma moment equal to 0.
So
Yes,
that
you can solve
then
this.
we can isolate, let's say AD and
Yeah,
A.
correct. Yes,
Sorry,
correct.
DAB, because we already know AX and AY.
Yes, correct.
Ah,
So basically, in order for us to solve for the member uh, uh, at one particular joint, okay, for members which is which is happening at one particular joint, the external forces there must be known first. For example, here 5,000 Newton is known. That's why we can solve. We can solve for joint C. But at joint A and joint B, because the external forces AX and AY, BY is not yet known, we will not be able to solve it. So that's the first thing. You're supposed to know about the external forces first. Find the external force. At that joint that you want to solve. Then after that, you have to ensure as well the joint that you want to solve must only have two unknowns. two unknown only. Why two unknowns? Because at each joint, okay, we not look at this way. At each joint, for example, at joint C, we only have two equations, sigma fx, sigma fy equal to 0. Because there will be no moment there, no sigma moment there, sigma moment equal to 0 there, that we can use. So we can only use these two, sigma fx equal to 0 and sigma fy equal to 0. That's why we can only solve for two unknowns. That's why it's correct. Just now, Matthew said that, oh, we can solve for FCD. We can solve for FBC by solving joint C here. Because from joint C, we can draw the free body diagram like this. 5,000 Newton. Then we have FCD here. Then we have FBC here. Remember that the angle you're supposed to draw it correctly, right? Based on the known angle here and all the data that we have here. Because it's become a geometrical problem. By using joint C here, we will be able to solve for FCD and FBC using this. Correct? Rafi, correct or not, Rafi?
Yes, sir.
Yeah, correct or not? Can we solve for FCD and FBC though?
FC, I think so.
Yeah.
Yeah.
Because we have two unknowns and we have two equations, so we can solve it. After solving for this and this, after solving for FBC and FCD, then we can try to take a look at the other point. Oh, now we can try to solve for point D because FCD is known already. So we can solve for AD here and BD there. Remember, each joint we can only solve for two unknowns. So you have to do it step by step. Okay, because it's time's already up. I think I will give you some homework for you to practice more. Some basic homework for the trust. Okay, some basic homework for the trust and some advanced homework about the equilibrium. Okay, I think that's all for today. Don't forget to submit the homework by Thursday next week before the class. Okay, I think that's all for today. Okay, thank you very much for listening.
Thank you, sir.
Thank you, sir.
Thank
Thank
you,
you,
sir.
thank you, thank you.
Thank you, sir.
Thank you, sir.
Bye bye.
Thank you, sir.